Hi, in this video we will see the electrochemistry second part. Standard electrode potential. Standard electrode potential is the potential which is measured at the unit concentration and at 298 Kelvin. That is, it is measured in 1 molar concentration of electrolytic solution and at 25 degrees Celsius. This table represents the standard electrode potential of various molecule and ions, and the standard electrode potential are represented as E0 in terms of voltage. If the values are increased, if the E0 values are increased, then its corresponding oxidizing power will also increase. And the fluorine has the highest E0 value, then the fluorine is said to be a strongest oxidizing agent. Since it has the highest E0 value, it is said to be a strongest oxidizing agent. What is oxidizing agent? Oxidizing agent is the one that makes the oxidation of other metal, and this one is get reduced. And in contrast, if the values are decreased, lithium shows the least value of minus 3.05 voltage, that is in a negative voltage, then it is said to be a strongest reducing agent. What is a reducing agent? It reduces the other metal ion, and the lithium get oxidized, right? And if the electrode potential is positive, that is a higher potential, it can oxidize the hydrogen. If the electrode potential is negative, it can reduces the hydrogen ion to hydrogen. That is, higher potential has the ability to oxidize the lower potential. Remember that if the E0 values are higher, then the metals or atom has the oxidizing power. And if the E0 values are lower, then the atoms or metal has the reducing power. How would you determine the standard electrode potential between the magnesium ion and magnesium? So it can be determined when you connect it with a reference electrode of standard hydrogen electrode. See, any unknown electrode potential can be determined when you connect it with the standard hydrogen electrode, because the cell potential which is shown by the meter in the galvanic cell, which is equal to the standard electrode potential of that unknown metal. So it can be determined when you connect it with the standard hydrogen electrode. Can you store the copper sulfate solution in a zinc pot? No, you cannot store the copper sulfate in a zinc pot. Why? Because zinc is having the lower potential, whereas the copper is having the higher potential. So zinc is easily oxidized by copper. So after some time, all the zinc ions will be moved in the solution. Okay, from the zinc to zinc ion, it can easily oxidize. Oxidize means it will be changed into the zinc ion. So the copper solutions are mixed with the zinc ions. So you cannot store because it will be contaminated by zinc ion. So I can ask the reverse question. Can you able to store the zinc sulfate in a copper pot? Yes, you can store. Why? Zinc cannot able to oxidize the copper. Okay, zinc sulfate can be stored in a copper pot. Okay. Consult the table of standard electrode potential and suggest 3 substances that can oxidize ferrous ion under suitable conditions. If you take the table of a standard electrode potential, ferrous ions has a standard electrode potential of 0.77 voltage, and many substances are having a higher potential than this potential 0.77. So you have to see the higher value than the ferrous ion. So I have taken 3 substance, that is a 3 molecule bromine, chlorine and fluorine, are having the higher potential than the ferrous ion. So you can also take other substance like cobalt ion, and other thing also you can take it. Nernst equation is used to find out the electrode potential and the cell potential. Previously we have seen only the standard electrode potential values, not the electrode potential. Standard electrode potential is the one which is maintained in 1 molar concentration of electrolyte at 298 Kelvin. But for electrode potential, the ion concentration will vary, because whenever the electrode is connected with the other electrode, the reaction will start, and hence there will be a variation in the ion concentration. In anode compartment, there will be a generation of ions, and hence the concentration will increase, whereas in the cathode, the concentration of ions will decrease, because the copper ion is attached to the copper, as we have seen in the galvanic cells. Okay, and hence there will be a decreased concentration in the cathode compartment. So the variation in the ions will result in the change in the potential. As a general, the metal is in the reduced form. We have seen the standard electrode potential, that is oxidized form to reduced form. In the standard electrode potential table, you can see the metal ion is changed to metal, that is oxidized form to reduced form. Similarly, I have written as a M plus ion, which is added to the electron, and it gets reduced form. So the equation is, to find out the electrode potential, is E between the metal ion and the metal. E is equal to E naught minus RT by NF ln of metal concentration to the metal ion concentration, that is a product concentration to the reactant concentration. Which is a product? Metal is a product. In the equation, first equation, I have given the metal as a product and the metal ion as a reactant. Product concentration to the reactant concentration, right? Similarly, for the cell potential, E cell is equal to E naught cell minus RT by NF ln of product concentration raised to the stoichiometric proportion divided to the reactant concentration raised to its stoichiometric proportion. And what is N? What is F? N is the number of electrons involved in the reaction. Say for an example, if you take the zinc and the copper, the number of electron involved is 2 electrons. If you consider the aluminium, it will be the number of electron will be 3. If you take the alkali metals, it will be 1 electron. So the number of electron which involves in the electrochemical reaction. F is a Faraday constant. Faraday constant is nothing but 1 mole charge of electron. What is 1 mole charge of electron? The charge of 1 electron is 1.6 into 10 to the power minus 19. And the 1 mole of electron is 1 mole is 6.022 into 10 to the power 23. Multiply with the charge, you will get the value of 96,487 coulomb per mole. Per mole of electron is having the charge of 96,487. So you have to remember these things. What is a Faraday constant? You should definitely know this. And R, you know that it is a gas constant of 8.31 and temperature which is maintained in 298 Kelvin. So the Nernst equation is used to find out the electrode potential or the cell potential when the concentration of electrolyte is not equal to 1 molar, right? Before going to Nernst equation, we should know what is potential, why the potential is developed in the electrode as well as in the cell. For this, the two scenarios I have created. One is the potential difference between the 2 points. Okay, first we will see the potential difference between the 2 points. See, before that, the potential will not develop when there is an equal energy between the 2 points. So if you consider the 2 points as I have shown in the figure, 0 volt and 5 volt. So the potential difference is higher potential minus lower potential. 5 minus 0 is 5 voltage. The potential developed between the 2 points is 5 voltage, whereas the same thing I have given below, but there is no lower potential. Both the points are having 5 voltage and 5 voltage. So there will be no potential will be developed. 5 minus 5 is 0. So if there is an equal energy means the potential will not develop. Potential will develop only when there is an unequal energy. Okay, that is why see in the another scenario I have shown two buildings. One building is a short building and another one is a long building. The example I have taken is a copper electrode versus silver electrode. Copper electrode versus silver electrode. Copper electrode has the potential of 0.34 voltage. That is the potential difference between the copper ion and the copper is 0.34 voltage. Whereas silver is having the electrode potential between the silver ion and the silver 0.8 voltage. So these has a two various potential, and when you connect the cell, then the potential difference is between the higher potential minus lower potential, that is 0.8 minus 0.34, which I have shown is a 0.46 voltage. That is the rest of the height of the building is the energy difference. Okay, energy difference is the potential developed in the cell. And in the equation you have also seen ln. Ln is a natural logarithm having the base at 2.7. Whenever if you convert the natural log to logarithmic part, the log is one which is having the base 10. Okay, if you convert a ln to ln to log, you have to multiply with the value 2.303, because if you substitute 2.71 raised to the power 2.303, you will get the value of 10. The log 10 is 1. Okay, so if you substitute, if you convert the logarithmic part to log, means you have to multiply with 2.303 and substitute all the values, constant values, and 2.303. Okay, R value, T value, F value multiplied to the 2.303, you will get 0.059. Only thing is we should know the n value. N value will differ. Remaining all the values will not differ. Hence you can calculate the electrode potential using these values. To find the electrode potential using the Nernst equation, we should know E naught value. E naught values are determined at 1 molar concentration of electrolyte. Okay. But in the logarithmic part, we should know two concentration. Apart from metal ion concentration, we should also know the metal concentration. See, the metal concentration will not vary. Okay, for any metal, the concentration of metal will not vary, because the metal concentration is a solid. The solid concentration will not vary. Number of substance per unit volume is the solid concentration. That is mass per volume is equal to the density. The density of metal will vary. The density of metal will not vary for any size of metal. Okay, either it is a thin or thick. The density will not vary. Okay, the density of metal will not vary. If you make the bigger size of metal into a piece, small pieces, you will say the masses are decreased. But I will say the corresponding volume is also decreased. Let me take an example, the bigger iron which is made into a pieces, that is in 1 meter cube of metal has some mass. If you make it into a pieces like 1 centimeter cube, okay, You say the masses are decreased. I will say the volume is also decreased from 1 meter cube to 1 centimeter cube. So the corresponding volume will decrease and hence it maintains the same density. If it has the same density, then the concentration will also be equal to that. So the concentration of metal will not vary. You have to substitute 1 for that. Okay. Only thing is we should know the metal ion concentration in this equation. Nernst equation for cell potential. To find the cell potential, we should consider the galvanic cell. Galvanic cell of zinc versus copper. We have seen the example of zinc versus copper electrochemical reaction. Okay. And in that cell we should always maintain 1 molar concentration before the starting of experiment. Okay, before the experiment it should maintain that 1 molar concentration of zinc sulfate in the anode compartment and 1 molar of copper sulfate in the cathode compartment. And immediately after the reaction the electrolyte concentration will also vary. That is, the zinc ion concentration is increased in the anode compartment because zinc solid is converted into zinc ion. So the number of zinc ion is increased in the anode and the number of copper ion is decreased in the cathode because the copper ion is converted into copper solid. So concentration is varied in both the compartment from 1 molar. If the concentration of electrolyte is varied means then the cell potential will also vary. Cell potential is calculated by the formula ER minus EL, that is cathode potential minus anode potential. If we want to say exactly means higher potential minus lower potential. As we have already seen the two buildings, to understand the cell potential, that is the potential, we have seen two different height of buildings. The height of buildings, if the height of buildings varies means the energy is also varied. If you throw a ball from the height of a lower building means it has a lower energy. If you throw a ball from the height of higher building means it will have the higher kinetic energy. Okay, higher potential energy because mgh, potential energy has the formula of mgh. If the height varies means the energy will also vary. Similarly here also the energy depends upon the potential difference. Okay, here the energy is electrical energy. Since the cathode is having the higher electrical energy than the anode, the difference between the two electrodes shows the resultant energy in the terms of potential. Okay, resultant energy in terms of cell potential, that is in the potential. So as a result, I have substituted the electrode potential for the copper as well as for the zinc and rearrange the equation. We will get the E naught of cell, and I have also written as E naught of copper. See, we should always write the standard electrode potential as between the copper ion versus copper, that is between the metal ion versus metal, not only for the electrode. I have written as an electrode. For understanding purpose I have written like this, but you should represent as a metal ion versus metal. Okay, in the last equation I have given a cell potential of zinc versus copper, that is E naught of cell minus 0.059 divided by n log of zinc ion by copper ion. The n is the number of electron involved in the reaction, that is 2 log of zinc. Here you have to see the log of zinc ion concentration to the copper ion concentration. What is the zinc ion concentration? Zinc here, the zinc is oxidized to zinc ion, that is oxidized species in the numerator. The copper is reduced. The copper ion is reduced to copper. The copper ion concentration as a reduced metal. The oxidized metal is a zinc metal, reduced metal is a copper. Hence the general formula I have written in the highlighted in the blue color, the left hand side. E cell is equal to E naught cell minus 0.059 divided by n log of oxidized metal. Oxidized M is oxidized metal raised to the stoichiometric proportion. If they given the number of moles or 2 moles or anything, means depend upon the numbers you have write in the power, divided by the reduced metal ion concentration, not the metal ion concentration. Now I have written as a metal ion concentration raised to its stoichiometric proportion. So on the whole, the anode compartment, the ion concentration is increased, whereas in the cathode compartment the ion concentration is decreased. Always remember that you should write in the logarithmic part oxidized metal ion concentration to the reduced metal ion concentration raised to its corresponding stoichiometric proportion. Okay, oxidized metal ion concentration should be written in the numerator, reduced metal ion concentration should be written in the denominator. And in depth you can see the other things. You can visualize the cell potential through this mathematics. How? Here the zinc ion, as I have also given in the zinc ion concentration, that is increased. When you substitute in the zinc ion concentration in the logarithmic part, the values will be negative value. The negative value is increased. In the controversial to this, the copper ion concentration is decreased. That is, if the denominator value is also decreased, means the logarithmic value is getting increased. If the negative value is increased, means then the cell potential will decrease. That is, you can visualize that whenever if you start the reaction, means it shows the 1.1 volt initial. But after the reaction starts, means it will start decreasing the potential. 1.1 volt to 1 volt, 0.9, 0.8, because the ion concentration is keep on increasing for the zinc. The copper ion concentration is keep on decreasing. Negative value, what it makes? It subtracts the value. 1.1 to minus of something is the value. So you should have that such kind of imagination. See, you should not keep on remembering the things. If you have the imagination, means you can easily understand the concept. Okay, else it will be harder for you. You should have imagination. See, imagine like this. Whenever if you imagine a galvanic cell in front of you, you just have the visualization that in the anode compartment the ion concentration increase, means you should visualize that the color of the intensity is increased. You should imagine like this. Okay, you can imagine like this, and the color of the intensity in the cathode compartment is decreased. So increased intensity concentration means ion concentration is increased. Decreased color concentration means decrease in the ion concentration. From the equation you know that the oxidized species to the reduced species. So the numerator part is increasing, and hence the negative values are increasing. Because of that result in the decrease in the cell potential. The meter will start showing the decrease in the cell potential. Okay. In this question, the electrochemical reaction between the magnesium and silver. So magnesium here is oxidized. It loses the 2 electron and become magnesium 2 plus ion. Whereas the silver gains the electron, thereby it has a reduction process. It reduced it to silver solid. Silver ion to silver solid is a reduction process. So you know which is oxidized species and reduced species. Substitute their corresponding concentration. They have given the concentration. Okay, and here you can see the other thing. Silver has 2 moles. 2 moles of silver is they have given. 2 moles means it should be raised to its stoichiometric proportion. In the logarithmic part, I have given in the third step, silver ion concentration is raised to the power 2 because of the 2 moles involved in the reaction. and the number of electron involved here is 2 electrons. Not only to see the Ag plus has only 1 electron, but multiplied by the 2 into plus 1 is 2. So you should write n is equal to 2, not 1. Okay, substitute the n values, substitute the concentration value, you will get the resultant value of cell potential. Okay, and you see the cell potential was decreased. Why the cell potential was decreased? Any idea? As I have already said, the oxidized species concentration here is increased. See, the magnesium has 0.13, but the silver ion here is 10 power minus 4 molar, which is a very lower concentration. If the denominator is lower, less means, then the corresponding logarithmic value is higher. If the logarithmic value is higher means it is in the negative value. Then the negative value higher means the cell potential will decrease. You should have that imagination. Okay, you should have the visualization. To find the equilibrium constant from the Nernst equation, we are seeing the reaction between the copper versus zinc for the electrochemical reaction. If there is a starting of the reaction, then there will be an ending of the reaction. That ending point is called as equilibrium state. In that equilibrium state, you can calculate the equilibrium constant. Equilibrium constant Kc value can be determined by product concentration to the reactant concentration. So, if the reaction becomes at equilibrium state, the zinc ion concentration will not vary, copper ion concentration will not vary, hence it will be equal to the Kc value. Okay, substitute the Kc value, and remember that the cell potential I have have written as a 0. Why it is a 0? Because as I already said, whenever there is a starting of a reaction, the cell potential will start decreasing. Okay, because of the logarithmic part, negative logarithmic part, the values of logarithmic part will continuously increases, because the zinc ion concentration will continuously increases, as well as the copper ion concentration continuously decreases. On the whole, the negative logarithmic part will start increases. Negative value increases means it will be subtracted from the E cell value. That is 1.1 volt will be decreased from 1.1 to 1, 0.9, 0.8, 0.7, 0.6. At one point it becomes 0. That is at the equilibrium state it becomes 0 volt. Okay, then there will be a no potential. The reaction will stop. So I have written as a cell potential as a 0 in that Nernst equation. We know the standard cell potential, which is 1.1 for the reaction between the zinc versus copper. Substituting all the value, n value we know 2. Number of electron involved in the reaction is 2. Before the last step, I have written a log Kc is equal to 37.288. Whenever the log moves from the left hand side to right hand side, it becomes exponential form. See, log has the base of 10. Natural log has the base 2.7. Log has base 10. So, whenever the log moves from left hand side to right hand side, it becomes 10 power. Okay. So, I have written a Kc is equal to 10 power 37.288. You can also write it as 37 plus 0.288 is equal to 37.288. Okay. Then it is a power addition. Power addition can be separated as a power multiplication. Okay. That is 10 power 37 into 10 power 0.3. In previously you have learned this thing. If there is a multiplication, power things can be added. Okay. What is 10 power 0.3? We know the log of 2 value is 0.3. That is, I have written that box. See that box. Log moves from the left hand direction to right hand direction. Log 10 power 3 is equal to log 2. Okay. So 2 into 10 to the power 37 is the value for the equilibrium constant of the cell reaction between zinc versus copper. You can easily determine through the Nernst equation. So on the whole, if you want to calculate the Kc value, that is the equilibrium constant for any reaction, you have to know only the standard cell potential. Remaining thing, the n values are obtained by knowing the equation, and substituting all the values you will get the Kc value. It is a very simple process. It is a simple method to identify the Kc value for any reaction. Calculation of Gibbs free energy in a electrochemical reaction. Here also, to find the delta G value is difficult, because in general delta G is equal to delta H minus T delta S. That is, you should know four values. The H2 value, H1 value will give the delta H value. S2 value, S1 value will give the delta S value. So you should know four values. But here, with the simple formula, you can calculate delta G value only by knowing the cell potential. Delta G is equal to minus NFE cell. That is, N is a number of electron involved in the reaction, F is a Faraday constant, 96,486 coulomb per mole. Okay. So both the values we know. Only thing is we should know the cell potential. If we know the cell potential, you can calculate the Gibbs free energy. So for a reaction, if you maintained both the electrolyte concentration at 1 molar, then 1 divided by 1 raised to its stoichiometric proportion will be 1. Then the log value is 1. Log of 1 is 0. 0 into anything is 0. Then the cell potential will be equal to the standard cell potential. Substitute the E cell value of E naught cell in the equation, in the above equation. You will get the standard Gibbs free energy for a reaction. So delta G is equal to minus NF E naught cell, and it will be equal to the minus RT ln Kc. That is, substitute that minus NF E naught cell, you will get the E cell is equal to minus RT divided by NF into ln of Kc. Okay, then you can further simplify it as a minus 0.059 divided by n log of Kc value. Okay, remember always that when the ln is converted into log, you should multiply it with 2.303. The ln value is base 2.7, log value is base 10. Calculate the potential of hydrogen electrode in contact with a solution whose pH is 10. So they have given the pH value. Okay, pH is 10. If they are given the pH value, means you should calculate the hydrogen ion concentration. What is the pH? pH is equal to negative logarithm of hydrogen ion concentration. Since they have given the value of pH, substitute the value 10 is equal to minus log of hydrogen ion concentration. Minus is moved to the left hand side from the right hand side, and when the log moves from the right hand side to left hand side, means, as I have already said, log has the base of 10. Okay, if moves from the log form to left hand side, means it will move, it will convert into the exponential form. That is 10 power of that value, 10 power of minus 10. So the hydrogen ion concentration is 10 power of minus 10 molar. Okay, they are asking the potential of hydrogen electrode. What is the potential? The potential can be calculated through the Nernst equation. E is equal to E naught cell. E cell is equal to E naught cell minus of 0.059 divided by n. N here is a 1. Okay, log of 1 divided by hydrogen ion concentration. Substitute the hydrogen ion concentration, 10 power minus 10. Okay, since the standard cell potential is 0 for the hydrogen, you substitute 0 for the E naught cell. Substitute 0 minus 0.059 log of 10 power 10. The denominator, if comes to the numerator, means it becomes the power of plus 10. Then substitute the, if the 10, the power 10 comes to in the front. 10 into log of 10. Log 10 value is 1. 10 into 1 is 10. 10 into minus 0.59 is minus 0.59 voltage. Calculate the EMF of cell between the nickel and silver. Here nickel is oxidized, silver is reduced. They have given the cell potential, standard cell potential, that is 1.05 voltage. They are asking EMF. EMF is nothing but E cell, that is the cell potential. Since you know the Nernst equation, E cell is equal to E naught cell minus 0.059 divided by n log of oxidized species to the reduced species concentration raised to its stoichiometric proportion. Okay. Then n value here is 2 because nickel has a 2 lost his 2 electron to silver and silver gains a 2 electron. So n value is 2. In the logarithmic part, oxidized metal ion concentration here is nickel. Nickel concentration they have given in the bracket 0.16, whereas the reduced metal ion concentration is silver 0.002 molar, and its stoichiometric proportion is 2. That is why in the bracket I have written as a power 2. Power 2. Then substituting the value, you will get the 0.91 voltage. Here I will ask the same question. Why the potential was decreased to 0.91 from 1.5? See, any idea? See, silver ion has the lower concentration than the nickel. Okay. So, the cathode compartment supposed to be in a higher concentration or at least equal concentration. If it is a 0.16 molar means, then both the concentration will be equal, then the cell potential will be equal to the standard cell potential. Both the log will be cancelled, the numerator and the denominator will be cancelled. Log 1 is equal to 0. 0 of anything will be 0. Then it will be equal to the cell potential. But here the silver ion concentration is very decreased. Okay, and hence the logarithmic part will be higher value. If it has a higher value, then it shows the reduced potential. The cell in which the following reaction occurs between the iron versus iodine, that is ferric ion is converted into ferrous ion and iodide is converted into iodine. They have given the standard cell potential. They are asking standard Gibbs free energy, that is delta G naught, and equilibrium constant Kc value. They are asking both the thing. You know delta G naught is equal to minus NF E naught cell. They have given, since they have given the E naught cell value, substitute that with number of electrons involved here is a 2. So substitute the 2 in the n value. You know the Faraday constant 96,486 coulomb per mole into cell potential, standard cell potential. See, the charge multiplied to the voltage gives the work. Charge multiplied to the voltage gives the work in terms of joule. Okay, whatever the result you are getting here is joule per mole, because n doesn't have any units. E has a cell potential has a unit of voltage. Since the Faraday constant has the unit of charge per mole, that is C per mole. C per mole. C into charge into voltage is joule per mole. Since the delta G naught value is calculated in kilojoule per mole, it has to be supposed to be converted from the joules to kilojoule. When you convert the joule to kilojoule, you should divide by the 1000. If you divide by the 1000, you will get 45.54 kilojoule per mole. Units and all very, very important. You should not neglect it. And in the right hand side part, I have given the steps to calculate the Kc value. Delta G naught is equal to minus RT ln K. Here I have not substituted the delta G naught value, because if I substitute that value, I have to also substitute the R value, T value, and I have to convert the ln to log, multiply with the 2.303. It becomes more difficult for the multiplication. Since we know the E naught cell is equal to RT by NF into 2.303 log of Kc, by converting that same equation, see the steps, delta G naught is equal to minus NF E naught cell. Substituting the same thing, I have converted the same formula into the regular formula. E naught cell is equal to RT by NF into 2.303 log Kc. Since all the constant values are converted into 0.059 divided by n. N value here is 2, and calculating log Kc is equal to 7.98, and see that step, log Kc is equal to 7.986. Then the down step, I have moved the log value to the right hand side. Then the log has the base 10. 10 raised to the power of that value. 10 power 7.986. 10 power 7.986 can be written as 10 power 7 plus 0.986. And you can separate the 10 powers as a 10 power 7 into 10 power 0.986. Okay. Then 10 power 7 is written as it is, 10 power 7. 10 power 0.986 has been written as a 9.68. See, you can also easily calculate the power values of 0.986. I will explain later, because if I explain here, it will become lengthy video. So I will give the easy explanation, easy method to calculate the log of any log value by knowing 4 values. Conductance of electrolytic solution. Before going to the conductance, let me see some basics of electricity. Okay. In the electricity, you will study about the resistance. Resistance is directly proportional to length and inversely proportional to the area of that material. Okay. In the transformer, that is, if you take the example of a transformer, you can see wires and all. They will put a thick wire. Why? Thick wire has a lower resistance. Thick wire has a higher area, and hence it has a lower resistance, because area is inversely proportional. In the formula, area is inversely proportional. Hence, it has a lower resistance. If they put the thin wire, means it will have the higher resistance, and hence the heat will be generated. Even it will pick the fire. Because of that thing, they will put the thick wire. Resistance is equal to rho into L by A, where rho is resistivity of a material. What is resistivity? Resistivity will resist the current depend upon the material. Say if you take the copper has one resistivity, iron has one resistivity, silver has one resistivity, and even wood have one resistivity. So resistivity will vary for different material. Wood has higher resistivity. Here I have given the unit conversion for the resistivity. 1 ohm meter is equal to 100 ohm centimeter, or 1 ohm centimeter is equal to 0.01 ohm meter. You already know the unit conversions. That is 1 meter is equal to 100 centimeter, or 1 centimeter is equal to 0.01 meter. Why I have given this? Why they have given this? Because you will also come to learn the molar conductivity which is expressed in Siemens centimeter square per mole or Siemens meter square per mole. In one case you will multiply by 1000, and another case you will divide by 1000, which makes somewhat complex you to understand those things. In order to focus more on unit conversion, they have given like this, for the understanding purpose, not only for the understanding, to focus more about the unit conversion. Now conductance. Conductance is represented as a G. Conductance is inverse of resistance, that is G is equal to 1 by R. You know R is rho into L by A. Substitute those parameter, you will get 1 by rho is into A by L, where resistivity is inverse of conductivity. Conductivity is expressed in as a K in terms of Siemens centimeter inverse. The conductivity of the material are of three types. One is a conductor, second one is the insulator, third one is semiconductor. See the values of conductors, which is having the higher value into 10 power 3, whereas the insulators are expressed in the 10 power of minus 16. The semiconductors are between the conductivity value between the conductors and the insulator. And special category is there. That is superconductors. Superconductors are the one having the zero resistivity at 0 Kelvin. Generally, it will be having the superconductors at 0 Kelvin. But nowadays, some of the ceramics and the polymer materials, shows the zero resistivity even at a higher temperature of 150 Kelvin. Electrical conductance and the conductance of electrolyte. Electrical conductance is for the metal at solid state, whereas the conductance of electrolyte is for the metal ion at liquid state. Coming to the property of electrical conductance, first property is the nature and the structure of the metal. What is the nature of the metal? Nature of the metal can be varied for iron and copper. Copper has the higher conductance, whereas the iron has the lower conductance. The nature is differed. Okay. And the structure. Coming to the structure, imagine that iron is a thick. That is the area. It has a thick wire. That is the increased area means it has a higher conductance. If it is a thin wire means it has decreased conductance. And the second property is the number of valence electron per atom. Take the same example, iron. Iron has two state, ferrous state and ferric state. In the ferrous state, it has the valence electron of +2. Number of valence is +2. Whereas in the ferric state, the number of valence is +3. And the third property is temperature. Temperature, if increases the temperature, then it decreases the conductance. Conductance of electrolyte. First property is the nature of electrolyte added. What is the nature of electrolyte? Take an example of NaCl added to the water. It will split as a Na plus Cl minus. Cation has one nature, anion has another nature. The second property is the size of ion produced and the solvation. Take an example of alkali metals. Alkali metals has a +1 oxidation state, that is a plus lithium plus, sodium plus, potassium plus, but the sizes will vary from top to bottom. If the sizes varies means the conductance will also varies. If the sizes varies means the solvation will also varies, and hence there will be a different conductance for the different ions. And third property is the nature of solvent and its viscosity. Take the same example of NaCl. Put it in the oil. Oil is also a solvent which is having higher viscosity. If it has a higher viscosity means it has a decreased conductance, whereas in the water it has a increased conductance. So nature of solvent is also responsible for the conductance of electrolyte. And the fourth one, concentration of electrolyte. Take the same example, NaCl. If the NaCl concentration is maintained in 1 molar concentration and another concentration is 0.1 molar means the 0.1 has a lower conductance. And fifth property is the temperature. If you increases the temperature, then the conductance will also increases. Measurement of the conductivity for ionic solution. If you want to measure the conductivity for ionic solution, then you will face a two problem. First one, if you use the DC voltage across the solution, then the composition of solution will also varies. That is, the positive ion will move towards the negative electrode, the negative ion will move towards the positive electrode. Hence, you will not measure the proper conductivity of the solution. And the second problem, you cannot bridge the solution as like the metallic wire. But the two problems can be solved by below solution. That is, if for the first problem what I said, if you apply the DC voltage, apply the AC voltage. AC voltage is nothing but the alternating current. What is alternating current? One time it will act as a cathode, another time it will act as an anode. If you increases the frequency of the AC voltage, that is keep on switching the plus and minus, altering the both the plus and minus, the ions will move from here and there. But the positive ion will detach and moves towards the cathode, and the cathode to anode. It will move from here and there. Then at one point, it will have the equal ion. That is, it has the uniform concentration across the solution. Then it shows the correct conductivity of that ionic solution. And the second problem is solved by using the conductivity cell, where you have the specific area and the specific length. Then you will measure the conductivity of that position alone. The conductivity of unknown electrolyte can be determined by knowing two values. One is cell constant and another one is resistant. That is, kappa is equal to G star divided by R. And the cell constant can be determined by using L by A formula, that is the length and the area of the solution. See, I have given the figure, the length and the area shows the cell constant. But you cannot use the length and the area measurement, because the length whatever you measured will be the correct and accurate, but the area of the solution is difficult to measure it. And also it will be an inaccurate value to find out the G star value. Okay, how you can find out the G star value? You can find using the other formula, G star is equal to R into kappa. By knowing the resistance and the conductivity of a known solution like KCl, you can easily determine the cell constant. That is, G star value is equal to R into kappa. Shows the G star value. So you find out the G star value. Only thing is you have to find out the R value. If you know the R value, you can easily calculate the conductivity of the electrolyte. Okay, how you can measure the R value? R value can be determined by using the Wheatstone bridge. If you connect the conductivity cell in the Wheatstone bridge, you can calculate the R2 value by using the formula R2 is equal to R1 into R4 divided by 3. You can calculate it, because these are the resistant. We know that we can easily measure it. Okay, we know that resistant. Substitute the resistance value, you can calculate the resistance of unknown electrolyte solution. So you calculated the R value and you know the G star value, which gives the conductivity of unknown electrolyte. Molar conductivity. As we already seen, if the concentration of electrolyte varies, then the conductivity will also varies. And conductivity, if we expressed in terms of molar concentration, means then it is a molar conductivity, which has the symbol lambda m. You have already seen the lambda symbol in the wavelength. That lambda is a lowercase lambda and this lambda is a uppercase lambda. and the lambda m is kappa by C because it is the conductivity per molar concentration of electrolyte, right? Molar conductivity is conductivity per molar concentration of electrolyte, that is conductivity for 1 molar concentration of electrolyte. Okay, lambda m is equal to K by C. What is C? C is a molarity. Concentration is expressed in terms of molarity, where m is equal to N by V. See the last step I have given. Lambda m is equal to K by m. As you know, m is equal to N by V. Substitute the V. V is expressed in 1 liter. 1 liter of a solution will be equal to 1 decimeter cube of space volume. And the 1 decimeter cube is equal to 10 power minus 3 meter cube, as I have written in the left bottom of the box. I have written as, see that conversion of decimeter cube to meter cube and the decimeter cube to centimeter cube. For the decimeter cube alone I have written, you can substitute the similar method for the centimeter cube. For the meter cube, it was 1. The number of mole is 1 because the concentration is 1 molar. 1 molar means 1 mole to the 1 liter of solution. 1 I have, for N I have written 1, and for V I have substituted 10 power minus 3 meter cube, and this meter cube 10 power minus 3 meter cube will goes to numerator, that is in the first denominator, second denominator to first denominator, and it was converted to 10 power 3 meter cube. 10 power 3 is nothing but 1000, as it is shown in the formula, 1000 liter meter cube inverse. If you want to express the molar conductivity lambda m in terms of meter square, that is Siemens meter square per molar, means you have to divide by 1000. You know the molarity, you substitute the molarity concentration, that is a concentration you will substitute it, and you have to divide it by 1000. If you want to express the same lambda m in terms of centimeter cube, means you have to multiply by 1000. If you express in meter cube, means it is divided by 1000. If you express it in centimeter cube, means it is multiplied by 1000. And the conversion is also given in the right hand side. Centimeter cube to meter cube. Meter cube to centimeter cube. See that conversion. Coming to problem. Resistant of conductivity cell filled with 0.1 molar concentration of KCl is 100 ohm, and if the resistance of same cell filled with 0.02 molar KCl solution is 520 ohm, calculate the conductivity and molar conductivity of 0.02 molar KCl. Conductivity of 0.1 molar KCl solution is 1.29 Siemens per meter. So they have given two concentration. One is 0.1 molar KCl and another one is 0.02 molar KCl. And they have given the resistant. Corresponding resistance also they have given 100 ohm and 520 ohm. As I have highlighted the concentration as a C1, C2 and the resistance as a R1, R2. But they are asking the conductivity and molar conductivity only for 0.02 molar KCl, not for 0.01, not for 0.1 molar KCl, right? Since you have to calculate the for particular concentration, they have also given the conductivity for 0.1 molar KCl solution. So as I have already said, if you want to measure the conductivity for a particular electrolyte, means there are two steps. First step is you have to find the cell constant from the known solution. The known solution here is 0.1 molar KCl. Substitute the conductivity value. kappa is 1.29 as they have given, and substitute their corresponding resistant. Corresponding resistant is 100 ohm. This is for 0.1 molar concentration. So you are substituting that value. You find the cell constant. Now you know the cell constant value, which will not vary for any other concentration. It will be constant. It will not vary. And if you know, they have also given the resistant. Resistant is 520 ohm. Substituting that values, you will get the conductivity for 0.02 molar KCl solution. You got the conductivity because you know the two parameters. From the two parameter you can calculate it. Now for molar conductivity, you are substituting the concentration, and as I have already said, if you want to express in meter cube means you have to divide by 1000 and substitute the concentration 0.02 molarity multiplied by 1000. That means divided by 1000. You have to substitute the 1000 in the denominator, not in the numerator. If you want to express the same thing in centimeter cube means you can multiply the same value with the 1000. 0.248 divided by 0.02 into 1000 means it is expressed in Siemens centimeter square. Another problem. Electrical resistance of column 0.05 molar NaOH solution of diameter 1 centimeter and length 50 centimeter is 5.55 into 10 to the power 3 ohm. Calculate its resistivity, conductivity and molar conductivity. They are asking resistivity, and they have given a diameter of the solution and the length of the solution. As we know the resistivity using the formula, R is equal to, resistance is equal to rho into L by A, resistivity into length by area. So they have given the length of the solution and the area of the solution. Substitute the length and the area. Length they have given, but the area they did not given. Area of the solution can be calculated by pi r square. Pi, you know the value 3.14, and r square, r is the radius where they have given the diameter. As I have highlighted it as a 2r. Divide the 2r, divide by 2, you will get the radius. Radius will be 0.5. 0.5 and r square, if you make the square, it becomes 0.25 centimeter square. And multiply it, you will get the area. Substitute the area, length, you will get the resistivity because they have given the resistance of the solution. Rho is equal to RA divided by L. You will get the resistivity. And for the conductivity kappa is equal to 1 by rho. Substitute the rho value, you will get the conductivity. And for the molar conductivity, they have given the concentration. And you know the conductivity. Substitute the conductivity divided by molar conductivity. That is the concentration. If you substitute the concentration 0.05, you will get the value. Variation of conductivity and molar conductivity. We have seen many times that conductivity depends on the concentration of electrolyte. That is, it is directly proportional to the concentration. If you increases the concentration of electrolyte, then the conductivity will also increase. Okay, what about the molar conductivity, lambda m? Molar conductivity decreases when it increases the concentration because it is inversely proportional to molar conductivity. Concentration is inversely proportional to molar conductivity. You can see the formula, lambda m is equal to kappa by C. So concentration is inversely proportional. If you increases the concentration, then the molar conductivity decreases. Molar conductivity for strong electrolyte. Before seeing the molar conductivity, let us see the limiting molar conductivity. limiting molar conductivity is a molar conductivity at zero concentration. That is, at 0 molar of electrolyte, then the conductivity is said to be a limiting molar conductivity, which is lambda naught m. Right, coming to molar conductivity. If you decreases the concentration as shown in the graph, the molar conductivity increases. You should also remember the formula lambda m is equal to kappa by C. If the concentration decreases, then the lambda m value will increases because of inversely proportional. And you can obtain the lambda naught m value by extrapolating the line. If you extrapolated the line, you can get the lambda m value. It is not the measurement value, it is an obtained value. Remember it. And lambda m is equal to lambda naught m minus a into c power of half. This is basically a linear equation. See, y is equal to mx plus c is a linear equation. Which is y? Lambda m is y. Lambda naught m is a c value. Lambda naught m is a c value which is a constant. And minus a is the negative slope. C is the c power of half is the x value. Y is equal to mx plus c. And the a value depends on the type of electrolyte. That is, if you take a NaCl, it is 1:1. That is, it has a charge of +1 and -1. If you take the calcium chloride, it is 2:2 because it has a 2 plus charge and 2 into Cl minus. That is, it has -2 charge. When you multiply the -1 into 2, you will get -2. And for the magnesium sulfate, again it is a 2:2 because magnesium has a 2 plus and the sulfate ion is a 2 minus. In this problem, they have given concentration and the molar conductivity of KCl, and they are asking to determine the limiting molar conductivity and the A value for the KCl solution. But they are asking to make a plot and extrapolate the straight line to determine the lambda naught value. Since it is a easy process, you can easily extrapolate and calculate the value. It is an easy, but I will explain the other method that will make you to understand the straight line equation. The other method is which is not even given in the book. For the understanding purpose, I have given it. To find out the unknown value, you can use the known values, like you have to calculate the delta x value and the delta y value. Delta y minus delta x will shows the m value, that is a factor. M value is a factor. In the straight line equation, m is a factor. Y by x, that is the delta y by delta x, right? Here the delta y is delta lambda m. The delta x is delta c, that is c1, delta c1. I have calculated the value for the delta c1 and the delta lambda 1, lambda m1 values. In order to find out the difference between the least concentration of molar conductivity, that is 148.61 to 0 concentration, then the C2 value is 0.01407, right? It is a delta lambda m2 value you have to determine for the concentration of 0.0147. That is, you have to determine the x value for the y value. Okay, you know the x value, but you don't know the y value, unknown y value. You are calculating by multiplying the factor. The factor I have mentioned in the box. If you multiply it, you will get the delta y value. Okay, the delta y value is increased from 148.61, right? Then you have to add that value, right? Then you will get the corresponding value of 150, which is given in the book. Molar conductivity for weak electrolyte. Here also the molar conductivity increases for the decrease in the concentration. If you decreases the concentration, the molar conductivity will increases, because molar conductivity is inversely proportional to concentration. The typical example here, the electrolyte is acetic acid. Acetic acid is a weak acid, right? It has a degree of dissociation is very less. And here you have another problem. You cannot able to find out the limiting molar conductivity for this electrolyte. Why? Because it is not a straight line curve, it is an exponential growth curve. Okay, you cannot extrapolate it and calculate the limiting molar conductivity, but you can determine the limiting molar conductivity by knowing the degree of dissociation of alpha is equal to lambda m divided by lambda naught m. Kohlrausch law. Kohlrausch performed some of the experiments for the limiting molar conductivity of various electrolytic solution by maintaining the same anion and same cation for the different set of experiment. In the first set, he maintained the same anion. See, the lambda naught m of KCl minus lambda naught m of NaCl in the first set experiment. That is, the resultant will shows the Cl ion are same. If you subtracted it, the Cl will cancel, and the resultant it will shows the K minus Na, that is the potassium minus sodium, and the second set shows the KBr minus NaBr. Br will cancel and it shows the K minus Na. Similarly for the potassium iodide, sodium iodide, it also shows the K minus Na. All the K minus Na will shows the similar value. And the other set of experiment, by maintaining the same cation, maintaining the sodium will cancel. It shows the Br minus Cl in the second equal part, and it shows the approximate value of 1.8. That is a constant value. Hence, he concluded that the individual ion plays a major role for the limiting molar conductivity of electrolyte. That is, the limiting molar conductivity of electrolyte is the sum of limiting molar conductivity of individual electrolyte. That is the limiting molar conductivity of cation plus the limiting molar conductivity of anion. Here you have to remember that the lambda m value is a uppercase in the left hand side of electrolyte solution, but in the right hand side it was a lower case. Lambda naught of Na is a lower case, in the left hand side it is a uppercase. Remember that one. Calculate the limiting molar conductivity for calcium chloride and magnesium sulfate. Already they have calculated the limiting molar conductivity for individual ion, and they have given in the table. Only thing is you have to calculate the limiting molar conductivity for that particular electrolyte. If you take the CaCl2, that is a calcium chloride, according to the Kohlrausch law, it is an individual contribution of ion, that is a limiting molar conductivity of cation plus limiting molar conductivity of anion. Here the chlorine ion is 2, it has a Cl2, then you have to multiply by 2 into the molar conductivity of chlorine, right? They have given the value, you can substitute the value and calculate, means you will get the resultant value. Similarly for the magnesium sulfate, only thing here you have to understand is you have to know the formula and accordingly you have to substitute. Here in chlorine you have to substitute 2 into the limiting molar conductivity of chlorine, because the chlorine is Cl2. In this problem they have given the limiting molar conductivity of NaCl, HCl sodium acetate. Na is a sodium, Ac is a acetate ion, and they have given their respective values. They are asking the lambda naught value for the acetic acid. H is a H plus ion, Ac is a acetate ion. They are asking the limiting molar conductivity for acetic acid. So it is a sum of individual ion contribution, sum of H plus ion and the acetate ion, but you don't need the sodium ion and the chlorine ion. You can subtract, you don't need means you can subtract the sodium and chlorine. If you subtract the sodium and chloride, the individual ion contribution gets subtracted from the sodium acetate and the HCl. In the HCl, the chlorine ion will cancel. In the NaAC, that is the sodium acetate, sodium will be cancelled with the NaCl limiting molar conductivity, and substitute the given values, you will get the resultant value. In this problem, they have given the conductivity for particular concentration of acetic acid, and they are asking the dissociation constant of acetic acid, but they are also given the limiting molar conductivity of acetic acid, that is a lambda naught m value of acetic acid they have given. You have to calculate the dissociation constant K. We know the formula K is equal to C into alpha square divided by 1 minus alpha, which we have learned from the chemical equilibrium. Where C is the concentration, alpha is the degree of dissociation for weak acid. So we don't know the alpha value, that is degree of dissociation, can be calculated by the formula lambda m divided by lambda naught m, that is molar conductivity divided by the limiting molar conductivity, where the molar conductivity is equal to kappa by C, that is conductivity per concentration. They have given the conductivity for the particular concentration, substitute the value, you will get the lambda m value for the acetic acid, and they have given the lambda naught m value, substitute that one, you will get the alpha value, that is degree of dissociation, you will get it, and substitute all the value, you will get the dissociation constant K. Why does the conductivity of solution decreases with dilution? Here you have to imagine the conductivity cell. In the conductivity cell, you have the length of solution and the area of the solution, which gives the volume of solution. Area into length gives the volume V. And with the dilution means you are decreasing the concentration. Decreasing the concentration means number of ions in that particular volume of solution will decreases. See, the ions are responsible for the conduction. Okay. If the number of ion is decreased means, then the conductivity will also decrease. That was the answer. Suggest a way to determine the lambda naught m value of water. It is very simple question, because water will split as a H plus ion and OH minus ion. And you know the limiting molar conductivity is the sum of individual contribution of limiting molar conductivity of each ion. That is the lambda naught value of H plus ion plus of lambda naught value of OH minus ion will give the resultant value. Just add the limiting molar conductivity of H plus ion and the limiting molar conductivity of OH minus ion, which is given in the table. In this problem, they have given the lambda m value of acetic acid at particular concentration, and they are asking the degree of dissociation and the dissociation constant. They have also given the limiting molar conductivity of each ion, that is H plus ion and the acetate ion. See, the carboxylic acids are weak acids. HCOOH is a methanoic acid, it is a weak acid, and hence you can determine the degree of dissociation. It is a weak acid means you have to determine the degree of dissociation. From the degree of dissociation, you can calculate the dissociation constant, because we know the formula K is equal to C into alpha square divided by 1 minus alpha. They have given the individual ion of limiting molar conductivity. Substitute the value, you will get the limiting molar conductivity of methanoic acid, and you can find the degree of dissociation by substituting the value of given value of molar conductivity divided by the limiting molar conductivity shows the degree of dissociation, and substitute the values C, alpha, you will get the resultant value. Electrolytic cell and electrolysis. In the electrolysis, we will use the external source of voltage, that is, we will use the external energy to bring the chemical reaction. And the main application of electrolytic cell is the purification of metal. In the industrial sector, they will use the electrolytic cell for the purification of metal. Here we can see how they will purify the copper using the electrolytic cell. The electrolytic cell was given in the figure. As shown in the figure, you see the before electrolysis. You have to consider, you have to fix the impure copper in the anode, and you will take the small cathode of pure copper in the cathode. Attach the impure copper at anode and the pure copper at cathode, which is maintained in the copper sulfate solution. Here the cell, all the cell are connected in only one compartment, because the copper ion has supposed to be deposited from the impure copper to pure copper. So since the anode makes the oxidation, it loses the copper ion. The copper ion comes from the anode, will get attached to the cathode. As shown in the figure, the thin rod is become thick after electrolysis. After electrolysis, the rod become thick, which means you will extracted the copper, impure copper, as a pure copper. You have converted the impure copper to pure copper. In the impure copper, you have the contaminated with other ions, other metal ion like potassium or something, other ion will be there. Those ion will not attach to the pure copper. So you can extract the yield of pure copper with a higher mass. Similarly, you can extract the sodium, magnesium, aluminium like this. If you connect the two electrodes, you have to apply the bias potential. You have to apply the over potential to bring the chemical reaction. Quantitative aspects of electrolysis. Just now we have seen the electrolysis process for the purification of copper. If you use the electricity, that is an external source of electricity, it makes the deposition of metal ion to metal. Thereby it increases the amount of metal. So he stated two laws. First law is about the amount of metal deposited at any electrode is directly proportional to the quantity of electricity. That is, in the formula you can understand the law. Weight is equal to the charge. What is a charge? Charge is the quantity of electricity. Q is equal to I into T. I have given I into T into the molecular weight. Molecular weight. If there is an increase in the molecular weight, then there will be the increase in the mass of deposition, right? And N is the number of valence electron. For alkali metal, it is a +1. For alkali earth metal, it will be +2. For aluminium and aluminium family and all, it will have +3. And divided with Faraday constant 96,486, you will get the amount of deposition of metal in the cathode, right? Faraday's second law. Before going to this law, let us see some of the terminologies like equivalent weight, gram equivalent, number of gram equivalent. What is equivalent weight? Equivalent weight is atomic mass or molecular weight divided by the valency of ion. That is, if you take the example of copper, if you want to find out the equivalent weight of copper, means the atomic mass of copper is 63.5 and the valency of ion is 2 because the copper is 2 plus. Substitute the value, you will get the 31.75 gram for the equivalent weight of copper. And coming to the number of gram equivalent, if the 31.75 gram of copper deposited to the electrode means, then it is said to be a 1 gram equivalent, weight divided by equivalent weight. The deposited weight is 31.75, the equivalent weight is 31.75. So 31.75 will cancel, we will get the number of gram equivalent 1, right? And if the 63.5 gram deposited means the number of gram equivalent is 2. So you understand what is equivalent weight and what is number of gram equivalent. Now coming to the second law. The second law is the amount of different substance liberated by passing the same quantity of electricity which is directly proportional to the chemical equivalent of that metal ion, right? To understand the second law, you can take an example of galvanic cell between the copper and zinc. In the copper there is a deposition, whereas in the zinc there is a liberation of zinc ion. See, whatever the amount of substance attached in the copper, that is the copper ion is attached to the copper, means the number of gram equivalent attached to the copper and the number of gram equivalent liberated by the zinc will be same. If 1 gram equivalent of copper is attached means, then the liberated zinc ion is also 1 gram equivalent. If the number of gram equivalent attached to the copper is 2 means, then the number of gram equivalent liberated by the zinc also 2. By using the same quantity of electricity. That is the law they are expressing. They are stating that law. And also see the formula. Weight divided by equivalent weight is number of gram equivalent. So the number of gram equivalent is same for the metal 1 and also for the metal 2. That is the law expressed in terms of formula here. Product of electrolysis. In the product of electrolysis, if you run a chemical reaction in an electrolytic cell, there may be you can expect a different product other than the interest of your product. That is, take an example of NaCl, electrolysis of NaCl. In the anode compartment, the oxidation will take place, cathode compartment, reduction will take place. So, this chlorine ion is oxidized in the anode compartment, whereas the sodium ion is reduced in the cathode compartment. Sodium ion is reduced to sodium. And in the parallel, water is getting oxidized to the H plus ion. And the H plus ion is reduced to hydrogen ion. See the respective potential. See, in the anode, if the potential is decreased potential, then that electrochemical reaction will perform. That is, water has a zero potential, whereas the anode has a higher, whereas the chlorine has a higher potential. See, the chlorine has 1.36 voltage, but the water has 0 voltage. Which one is lower? Water is the lower potential. In anode, which one is having the lower potential? That one will be the preferred. Similarly, see the cathode. In the cathode, sodium ion has a standard electrode potential of minus 2.71 voltage, whereas the hydrogen has a 0 voltage. Which one is a higher potential? Hydrogen is a higher potential, right? Hydrogen has a higher potential, whereas the sodium has a lower potential. But here the cathode, which one is having the higher potential, that will be performed, has a preference to perform here. So, these can be overcome by applying the over potential. As I have given the electrochemical reactions, some of the electrochemical reactions are kinetically slow. and if you make the over potential, that is a bias potential, the reaction of sodium chloride will happen. That is, the chlorine ion will get oxidized and the sodium ion will deposited on the cathode. Coming to problem, if a current of 0.5 ampere flows through a metallic wire for 2 hours, then how many electrons would flow through the wire? They have given the current and the time. What connects the current and time? Charge connects the current and time, and they are asking how many electrons, number of electrons they are asking, right? Now you are calculating the charge. See, always converts the time in terms of seconds. They have given in the hour. So hours is a 60 minutes into 60 seconds gives the seconds. How many number of seconds it will give? So you are calculated the Q value, that is charge in terms of coulomb, and you have to calculate the number of electrons involved in that coulomb, right? For that you don't know the number, but you know the number of electrons involved in the Faraday constant. By knowing that number, you can calculate this number. How? N is equal to coulomb by coulomb per mole, because the Faraday constant has a charge per mole, right? Coulomb will get cancelled, and the number of moles is equal to the number of moles of electron involved in the reaction. So you will get the number of moles, and since the number of moles you have get, it has supposed to be multiplied with Avogadro number. Avogadro number is 6.022 into 10 to the power 23. You will get the number of electron. Suggest a list of metals that are extracted electrolytically. We have seen the example of copper purification through the electrolytic cell. So the copper is one metal, and we have also seen the sodium and magnesium, aluminum is also purified by the electrolytic cell method. So these are the metals that can be extracted electrolytically. They will have the ore, they will extract the ore metal and make the purification through the electrochemical process. By that they are obtaining the purest form of metal. Consider the reaction of dichromate ion, which is reduced, and what is the quantity of electricity in coulomb needed to reduce 1 mole of dichromate ion. Since they have given the mole, number of mole, 1 mole, they are asking quantity, right? You know the formula, W is equal to I into T into the molecular weight divided by N into the Faraday constant, right? What is weight per molecular weight? Weight per molecular weight is N. N is, they have given the value 1 mole. Substitute the N in 1, right? And they are asking charge. Charge is a Q. Q is the charge. Q is I into T. So I into T is Q, right? And you know the number of electron involved in the reaction. Number of electron involved in the reaction is 6 electron. They have given in the equation. Substitute the 6. You know the Faraday constant. Multiply it. You will get the Q value. That is the quantity of electricity to reduce 1 mole of dichromate ion. Batteries. In the battery, the chemical energies are converted into electrical energy. Batteries are of two types, primary and secondary. In the primary battery, the reaction will happen only once. After the completion of reaction, it cannot be reversed by using external potential. That is, it cannot be reused. After the completion of reaction, the primary battery can't be reused, right? The typical example for the primary battery is dry cell battery. That is, the clock battery is a dry cell battery. And coming to the component of primary battery, zinc acts as a anode and carbon rod acts as a cathode, and in between that manganese oxide, carbon, ammonium chloride acts as a paste between that anode and cathode. Coming to the electrochemical reaction, in the anode part the oxidation takes place, cathode part the reduction will take place. So zinc is get oxidized and the electron moves to the cathode, where the reduction happens in the manganese oxide to manganese oxohydroxide. That is, it is reduced. The hydrogen was added means it undergoes a reduction. Okay, why this primary battery can't be recharged? Any idea? See, zinc is oxidized. It can be reversed. That anode part can be reversed by applying the external potential. But what about the cathode? You can reverse the cathode reaction? No, because the ammonia involved in the product will evaporated. So you cannot pick the ammonia and insert into the cathode, right? Mercury cell. Mercury cell is a primary battery. It generates a low current, and you can see the mercury battery in hearing aids, watches and all having a small battery. That battery is a mercury cell. It consists of zinc mercury amalgam acts as a anode and carbon as a cathode. In between a paste of mercury oxide will be there. And coming to the electrochemical reaction, in the anode zinc is oxidized and releases the 2 electron, liberates the 2 electron, and zinc becomes zinc oxide. Whereas in the cathode the mercury is reduced to mercury liquid, right? Mercury is a liquid, not a solid. Mercury and bromine are liquid, right? And it reduces to mercury liquid. It gains the 2 electron. Reduction is happened. The overall reaction is represented as zinc oxidized, mercury reduced, right? Secondary batteries. Unlike primary batteries, the secondary batteries can be recharged by applying external source of energy. That is external voltage. If you apply external voltage, the reaction can be reversed. Once the reaction has completed, the reaction can be reversed by applying the external voltage. But in primary battery, you cannot reverse the reaction, right? The typical example for the secondary battery is lead storage battery. And coming to the parts, lead acts as an anode and lead oxide acts as a cathode. Pb acts as an anode, PbO2 acts as a cathode. You can see in the reaction also, I have written as a Pb solid, PbO2 solid as a cathode, right? And coming to the electrochemical reaction part, lead is oxidized to lead sulfate. Pb is converted into PbSO4, and see the oxidation state, 0 oxidation to state to +2 oxidation state. That is, it loses the 2 electron. Oxidation occurs at anode, right? In cathode, the reduction will take place. The lead oxide is reduced to lead sulfate. Lead oxide has a +4 oxidation state. Now it is +2 oxidation state. Lead sulfate has +2, Pb +2, 2 plus, Pb 2 plus, right? Pb 2 plus, SO4 2 minus, +2 oxidation state, because it receives 2 electrons from the anode part, right? And hence the net reactions are given below by forming water, right? And we have maintained this battery with the 38% of sulfuric acid solution. When the reaction completes, the sulfuric acid will be dissociated as a sulfate, lead sulfate. After recharging, when you recharge, the sulfate will comes to the as a sulfuric acid, and the water will also split. Here the water will loses when you recharge. So whenever if you want to recharge, that is reuse the battery, you have to add the water. nickel cadmium cell. Nickel cadmium cell is a secondary battery, you can recharge it. Here cadmium acts as anode and nickel acts as a cathode. That is a nickel 3 hydroxide acts as a cathode. And in the anode part it gets oxidation. Cadmium is oxidized from 0 oxidation state to +2 oxidation state. It loses 2 electron. Is converted to cadmium oxide. Whereas the nickel trihydroxide is converted into nickel dihydroxide. That is a nickel 2 hydroxide. Nickel 3 hydroxide is converted into nickel 2 hydroxide. They will mention the oxidation state alone. That is a +3 oxidation to +2 oxidation state. It was reduced. And another example for the secondary battery is a lithium ion battery, where we are regularly using in our day-to-day life. That is, we are using in our cell phones, mobile phones and all, we are using lithium ion battery. In lithium ion battery, they will give the cell potential. See the picture I have mentioned, the 3.7 voltage is the cell potential, right, for the lithium ion battery. But when you have to recharge, means you have to apply the over potential, that is, you have to apply the extra potential, as I have mentioned in the charger specification. See the output voltage, it was given up to 12 voltage, 5 voltage, 9 voltage, 12 voltage. You can recharge up to 12 voltage. See, if you apply 5 voltage, it takes a long time to recharge it. If you apply 12 voltage, higher potential, if you apply, it will be recharged very quickly, right? Fuel cells, it converts the chemical energy into electrical energy. It has a high efficiency of about 70% than that of the thermal plants, because the thermal plants which converts the chemical energy into the heat energy, then only the heat energy is converted into electrical energy. Here it straight away converted into electrical energy, so it has a higher efficiency. And the chemicals involved in the fuel cells are hydrogen, methane, methanol. Those are the fuels that can be converted into electricity, right? Fuel cells. See the figure. The hydrogen gases are passed through the anode compartment and the oxygen gases are passed through the cathode compartment. And intermediate, that is between the hydrogen and oxygen, they maintain the solution at alkaline condition. That is, alkaline solution are added in between the two compartments, right? And coming to the electrochemical reaction, the hydrogen is oxidized to give the electron and it forms the water, because the H plus ion will join with the OH minus ion and it forms the water. And the electron will move to the cathode and the oxygen is reduced to form the hydroxyl ion. The overall reaction will generate the water. That is, the formation of water is occurred in the overall reaction with the voltage of 1.23 volt. The cell potential is 1.23 voltage for the formation of water, right? Corrosion. Corrosion occurs at the metallic surface, where the metal objects are converted into metallic oxides or the salts. That is, metal is converted into metallic oxide or its salts. The typical example is rusting of iron and the tarnishing of silver. What is tarnishing? Tarnishing is a fading of silver. It loses the luster property. Silver loses its luster property. How you can prevent the corrosion? You can prevent the corrosion by coating with some chemical like bisphenol, and you can use the sacrificial electrode. What is the sacrificial electrode? It will sacrifice and prevent the inner metal. We will see the mechanism of corrosion. Let us imagine a metal rod, that is an iron rod, on which the water molecule is placed over it, as shown in the figure. In the figure, they have the grey part is the iron part, whereas the blue part is the water molecule. And here there will be a two half cell. which one? Oxidation, there will be an anodic part, and the reduction, it will be a cathodic part. See, the Fe is converted into Fe2 plus, right? That one is an oxidation, it loses 2 electron, whereas the reduction, the oxygen molecule comes from the air and binds with the hydrogen ion present in the water molecule to form a water, right? And see its standard electrode potential. The standard electrode potential of iron is minus 0.44 voltage, whereas the standard electrode potential of water is 1.23 voltage, and the overall cell potential is higher potential minus lower potential. That is a standard potential of water minus standard potential of iron, right? And again you can see the another oxidation. The iron is oxidized to ferrous part, ferrous ion. The ferrous ion is again converted into ferric by combining with the atmospheric oxygen. It gives the Fe2O3. Fe2O3 is a ferric oxide, right? Write the chemistry of recharging lead storage battery, highlighting all the materials that are involving during the recharge. During the recharge they are asking, right? What in the discharging, it will convert the lead into lead sulfate, right? And during the recharging, then there will be a reverse reaction. Lead sulfate will be converted into lead, right? And the another important thing is, here you will add the water, because during the recharge the water molecule will be converted into sulfuric acid, and that time the water will hydrolyze. That is, water will loss. There will be a loss of water, and you have to add the water, right? Remember the recharging step. In the recharging step I have reversed the reaction, right? Whatever the reaction occurs in the discharging is just opposite to that of the recharging. Suggest two material other than the hydrogen that can be used as a fuel in a fuel cell. So they are asking the fuel, chemical fuel for the fuel cell. We have already seen the hydrogen as a fuel in the fuel cell, and methane, methanol, other hydrocarbons can also be used for the fuel cell. Explain how rusting of iron is envisaged as a setting up of an electrochemical cell. Of course, the rusting of iron is a electrochemical reaction. It is an electrochemical reaction, we have seen, because the iron is oxidized and the oxygen is reduced, and the overall cell potential is 1.67 voltage. Why? Because the iron has a lower potential and the oxygen, the formation of water has a higher potential. Hence, it shows the overall cell potential. That is, if you see the positive potential, then it is a spontaneous reaction. Then it is an electrochemical reaction, right? And the final important thing is, you have to summarize it with the concept map. We have seen the electrochemical cell. What is electrochemical cell? It is of two types, spontaneous and non-spontaneous. That is a galvanic cell, electrolytic cell. Galvanic cell is a spontaneous reaction, where in the electrolytic cell there will be a non-spontaneous reaction. Hydrogen electrode. Hydrogen electrode acts as a reference electrode and its potential is 0 voltage. With the help of hydrogen electrode, you can able to determine the unknown standard electrode potential of other metal ion, right? Because it is a 0 voltage, and the corresponding cell potential will show the standard electrode potential of that metal ion. Coming to oxidizing agent, reducing agent. If the electrode potential is, standard electrode potential is negative, then it has a reducing property, then it is said to be a reducing agent. And if the standard electrode potential is positive or higher value, then it has oxidizing power, then it is said to be a oxidizing agent. The strongest oxidizing agent is fluorine, whereas the strongest reducing agent is lithium, right? Nernst equation is used to find out the cell potential or electrode potential whenever the electrolyte concentration is not equal to 1 molar. If it is differed, the 1 molar concentration is differed, then you can use the Nernst equation to find out the cell potential or electrode potential. And by using the standard cell potential, you can able to find out the equilibrium constant and the Gibbs free energy, because you know the n value, you know the number of electrons involved in the reaction, where F is the Faraday constant, 96,486 coulomb per mole, right? And in the cell potential, always remember that oxidized metal ion concentration raised to its stoichiometric proportion divided by the reduced metal ion concentration raised to its stoichiometric proportion. Don't forget to put the stoichiometric proportion, right? Conductance of electrolytic solution. If you want to measure the conductivity, you should know the G star value, that is the cell constant divided by the resistance of the solution, right? Cell constant can be identified from the known solution, and you can substitute the resistant. You will find out the conductivity of solution, which is a kappa, and the molar conductivity. The molar conductivity should be expressed in Siemens centimeter square per mole. The lambda m is equal to kappa by C. Molar conductivity is lambda m, which is a kappa by C. That is a conductivity per mole. Conductivity divided by molarity, right? Since it is a molar conductivity, you have to divide it by its molarity, right? And limiting molar conductivity. What is limiting molar conductivity? Limiting molar conductivity is lambda naught m at zero concentration of electrolyte. For the strong electrolyte, you will extrapolate it and find out the limiting molar conductivity, which is a straight line equation. Whereas for the weak electrolyte, you can determine the limiting molar conductivity using the degree of dissociation, right? Electrolytic cell and electrolysis. This is mainly for the purification of metal. Copper is purified at cathode. Purification of metal is at cathode. The impure copper is placed at the anode, right? Quantitative aspects of electrolysis. It is about the Faraday first law and the second law. First law is the amount of substance deposited at any electrode is directly proportional to the quantity of electricity. That is, W is the amount of substance which is directly proportional to the Q charge. Q is I into T. If you make say equal the proportionality, you have to add the proportionality constant. The proportionality constant is molecular weight is a proportionality constant, Faraday constant is a proportionality constant, and N is also constant for that reaction. For that reaction, the N will not vary, number of electrons involved in the electrochemical reaction. And second law, the different substance liberated at the same quantity of electricity is directly proportional to the chemical equivalent weight, right? W1 by E1, that is equivalent weight, is equal to W2 by equivalent weight of other metal ion. Batteries. Batteries are primary battery, secondary battery. Primary battery not be rechargeable, secondary batteries are rechargeable. Example is dry cell battery, zinc amalgam batteries are primary battery, secondary batteries are lead storage battery. Coming to fuel cell, it will convert the chemical energy into electrical energy. Example, hydrogen is a fuel, methane is a fuel, methanol is also a fuel. Corrosion converts the metal into metal oxide. The surface of metal is converted into metal oxides or its salts. How you can prevent? You can prevent it by using the sacrificial electrode like zinc and tin. Thank you for watching the video. I have covered all the topics of electrochemistry and it will be more useful for the student who are preparing for board exams as well as for the competitive exams. And you can take your own notes from this video. You can pause the video and also take the notes. It will be more useful for you, and I will try to upload the exercise part as soon as possible. Thank you.